Hello everyone. Today we're going to talk about mean electrical axis, how to figure out the mean electrical axis by looking at an ECG strip. Let's take a look at an ECG or an EKG graph together. This is what you usually get when someone has an EKG done. And you usually see that there are a bunch of like letters, Roman letters right here, 1, 2, and 3, and then there's usually AVR, AVL, AVF, and then you have those 6 V's right here. Now, what do these represent? Those are representing the different leads, so we're going to go ahead and discuss it. But an EKG in general, what is it for? An EKG is going to measure your heart's electrical activity. It's going to be detected by electrodes placed on your skin. So you usually place negative and positive electrodes on your skin. You can place them on your wrists and on your ankles, or you can place them, instead of your wrists, you can put them on your arm, etc. It's just that you want to be consistent. So if you're going to put a negative electrode on your right wrist, then put the positive electrode on your left wrist. So if you're going to go with wrists, then go ahead and use your wrists. If you're going to use like shoulders, etc., just make sure that when you place those electrodes on the skin, you are being consistent in how you are placing them. And this is a very non-invasive, basically, technique. And this non-invasive technique is going to go ahead and help you detect if everything is normal with your heart's electrical activity, if everything is like your electrical conduction within your heart is normal, or if you are experiencing arrhythmias, or if you are experiencing a heart attack. The EKG can actually give you all of that information, and you get basically that graphic record right here. And this graphic record is going to be able to tell you the direction and the magnitude of your electrical activity generated by your heart when your heart goes through all of these action potentials. An EKG could actually be analyzed using 12 different leads. The first 3 leads, we refer to them as 1, 2, and 3. Those are called the bipolar leads. And you can see that for these 3 leads, you usually have a negative electrode and a positive electrode. So for example, for lead number 3, the negative is going to be on the left wrist and the positive is going to be on the left ankle, etc. So those are the first 3 leads that we usually use. And then we have another 3, we refer to them as augmented leads. And that's why you see AVF, AVL, so the A stands for augmented. So you have AVF, and it usually gives you a view from your heart going down this way. AVL is going to give you a view from your heart within that angle right here. And AVR is going to give you a view of your heart in this direction right here. As you can see, each lead is going to show you, and it's going to help you detect the electrical activity of your heart from different angles. Basically from 12 different angles, because you also put 6 right here on the chest. So if we say that here is the heart right there, you're basically getting information from all of these different angles. Okay, so guys, this is lead number 1. It's kind of showing you a view of your heart's electrical activity within this angle right here. AVF is showing you a view from this angle right here, kind of perpendicular to the heart. This is lead AVR. It's giving you a view from this angle right there. This is AVL. Okay, and then this is lead number 3. It's giving you an angle right here. So as you can see, you end up getting 12 different views of the heart. Now, these electrodes, when they are placed, by the way, on your skin, they are picking up the electrical activity of your heart. Those electrodes are not passing any electricity inside of you, okay? They're just picking up the electrical activity without passing any electricity into your body. And as I said, each lead is going to represent a particular orientation of your heart. It's going to show you a different view of your heart. Basically, all of these different views end up providing you with this EKG graph right here. You get the P wave, you get the QRS, and you get the T wave. We are going to discuss what it means by normal axis LAD, RAD in just a minute, but I wanted to show you right here. This is lead number 1, lead number 2, and lead number 3. Notice how these 3 leads right here, they end up giving you this triangle right here. Within this triangle, again, you're picking up all the electricity that's being conducted within your heart, and we end up calling this triangle right here Einthoven's triangle. That was the guy who actually came up with this, and he discovered it, so we call it the Einthoven's triangle. And again, this Einthoven triangle is giving you a view, right? It's giving you a view of your heart from different angles. Again, lead 1 right here, this angle, lead number 2 showing you from this angle, and then lead number 3 is showing you the heart from this angle right here. The electrical impulse usually originates in the SA node, which is right here within the right atrium, and then it travels from the SA node to the AV node, and then from there it's going to go to the bundle of His or the AV bundle, down the bundle branches, and then to the Purkinje fibers, and then the Purkinje fibers are going to conduct the electrical impulse to the outer surface of the heart. So therefore, the electrical impulse is basically traveling from the SA node all the way to the left ventricular apex. So the overall direction, if you think about it, the overall direction of the depolarization in a healthy heart should be headed downwards and towards the left. So let me go ahead and kind of highlight that for you. So basically the overall direction is going down, and it's going more towards the left. Now, that's what we refer to as the mean electrical axis. So the mean electrical axis is normally headed, as you guys can see, it is headed towards in a downward direction, and it's more towards the left. Now, if we think about it, each myocardial cell, right? Each myocardial cell in your heart must be depolarizing, right? So that it can enable the mechanical contraction. And that depolarization wave is reaching all the different cells in the heart. So what we are trying to figure out is basically an average or a mean of all of these combined depolarizations and repolarizations that we are measuring throughout, within the heart. And that's what allows us to figure out the mean electrical axis of the heart. So at the end, the mean electrical axis is like an average of all of the electrical activity generated. And we usually we're concerned about the QRS wave because the QRS wave it's relatively large in comparison to the other complexes, so it's easily measured. And because also, if you think about it, the left ventricle is larger compared to the right ventricle. So again, that's why we measure the QRS wave. So let's go ahead and discuss together how can you still determine the direction of your mean electrical axis or your mean cardiac axis, but normally it should be anywhere around in between -30 degrees to 90 degrees. So therefore, if it's anywhere in here, we usually refer to it as the normal axis. Let's discuss vectors. What is a vector? A vector is basically a force. And this force has a magnitude and it has a direction. And it's usually depicted by an arrow. And that arrow signifies the strength and the direction of that force. Every depolarized myocardial cell in the heart actually produces its own small vector. And if many of these cells within your heart, they get depolarized and they get depolarized in the same direction, the same time, you end up getting a large vector, and a large vector gets created. And when we go ahead and we figure out our mean cardiac axis, or you can refer to it as your mean electrical axis, basically that mean electrical axis is going to represent the net direction and magnitude of your electrical force. To kind of give you an example, so let's say here is lead number 1 right here. If you have a vector that's headed this way for lead number 1, and as you can see right here, down here is your lead AVF. Let's say you have a vector, an electrical vector that's headed this way right here, and I'm going to show you how you can tell the direction of the vectors in just a minute. But let's just say that you have a vector that's moving down this way in lead number 1, and you have another vector moving down this way right here for lead AVF. For you to figure out the mean of these vectors, what we go ahead is we draw in between, and that would be your mean electrical vector right here. So as you guys can see, the mean electrical vector is usually like around here. Now it doesn't always have to be 60 degrees. As I said, anywhere from -30 to 90 degrees would be where you should have a normal axis. And this has to do with physics. When you guys have a vector going this way, you draw the other vector right here, kind of perpendicular to it, and then you draw the mean vector in the middle, and that would be the mean electrical vector right here. Now, when we go ahead and we take a look at our EKG, remember how I said we're going to take a look at our QRS wave? So when you look at, let's say, right here, you guys have like the P wave right here. Here is the QRS complex, and then you have the T wave right there. Again, we're going to be concerned more about that QRS complex. Now, if the R wave, as you guys can see, so here's the R wave, okay, and here is the S, correct? So here's the R, here's the S, here's the T wave. Okay, and here is the P wave. Okay, we go ahead and we take a look at the R wave. Now, notice how the magnitude or the amplitude, okay, notice how the amplitude of the R wave, here's the amplitude of the R wave, notice how it's way larger compared to the amplitude of that S wave, okay? When the amplitude of the R is way larger than the amplitude of the S, we say that this is a positive deflection, okay? Meaning that the vector is headed towards the positive degrees, okay? And I'll show you an example. If the R wave and the S wave, they're equal, like you can't really tell, the amplitudes are about the same, then we say that this is equiphasic, meaning you're not going to have a positive or a negative deflection. If your R wave, notice how your R wave right here is way smaller compared to the S wave, we say that this is going to be a negative deflection, meaning again that your vector should be headed towards the negative side. Okay, if the R is larger than the S, then your vector is mostly going towards the positive side. If they're equal, then it's equiphasic and you don't get any deflections. This red line that I tried to show you right here, we refer to it as the isoelectric line, and basically this is when you don't have any deflections, okay? So you just have like a straight line. If you see on your EKG something like this, like it's going upwards, that is a positive deflection. And a positive deflection is usually when your vector is headed towards the positive electrode, right? If you get another kind of like line right here, that means, okay, no deflections are taking place. They're equal. If you see a downward deflection, the downward deflection meaning that you are moving away from the positive electrode. You are headed away from the positive electrode, and so therefore you get a negative deflection, okay? Now, how are we going to use the positive and negative deflections, etc., to figure out our mean electrical axis? We go ahead and we refer to our EKG. Now, this is a 12-lead EKG. So you have your lead 1, here's lead 2, here's lead 3, then you have your augmented leads right there, and then you have your chest leads. V1 through V6. Now there's so many ways of figuring out your mean electrical axis. One way is we go ahead and we take a look at lead number 1 and you take a look at lead AVF. So those are the two leads that you can view. You can also view other leads, but we'll discuss viewing lead 1 and AVF. Let's take a look at a few examples together to figure out the mean electrical axis if you are given an ECG strip. This ECG strip right here is showing you the electrical conductivity of your heart. It's graphing time on the x-axis and it's graphing voltage on the y-axis. As you can see, this ECG strip right here is showing you lead 1, 2, and 3, and it's also showing you the augmented leads AVR, AVL, and AVF. For this example, we are going to concentrate on lead number 1 and lead AVF. Now, can you use and can you look at other leads other than 1 and AVF? Yes, you can. But this is just one method of how to figure out the mean electrical axis by looking at lead 1 and lead AVF. You look at lead number 1, and if you take a look at lead number 1, let's just go ahead and take a look at it together. you can see that right here you have your P wave, here is your R, right here you have your S, and right here you have your T. Okay, and then of course right about here, it's just going to be hard for me to write it, but you have like your Q. Okay, so your PQRST waves right there. What you want to do is you want to figure out and you want to compare the amplitude of your R to your S. Okay, so if I go ahead and take a look at the amplitude of my R, I'm going to highlight it for you. So here's the amplitude for my R, and do you guys see how small the amplitude for the S is? So when your R, okay, when your R is amplitude is larger than your S, we say that this is going to lead to a positive deflection. And your electrical vector is going to be pointing towards the positive side. Okay, and I'm going to show you how you're going to present that on this hexaxial axis that we have right here, this circle with all the different degrees angles. I'm going to show you how you can interpret it on there. But let's take a look at the AVF. You're going to do the same thing. You're going to go ahead and take a look at the amplitude of the R wave, and you can see that the amplitude of the R wave, it is pretty large. So one more time, the R is larger than the S. One more time, that's going to cause a positive deflection, okay? And the vector is going to be headed towards the positive side. Now, what does that mean? It means you're going to take that information and you're going to find lead 1. So here is lead number 1. You are going to draw your vector this way. You draw the vector on this side if it's showing positive, okay? If it's headed towards the positive. And then you go ahead and you find your AVF. So here is your AVF, and I'm going to go ahead and draw my vector going down this way towards the positive 90, because again, I'm not going to go up and draw it up to the negative 90. Okay, guys, I'm not going to draw it up in the negative 90 side, because again, it's also positive. Okay, now to figure out the mean electrical axis, all you got to do is draw an arrow in between those two vectors, and that would be your mean electrical. I'm just going to abbreviate it to right here. So that's your mean electrical axis right there. Okay. Now, there is another way of doing it instead of drawing out the vectors this way, which I think is really the easiest way. There's also a way called the quadrant method, where they go ahead and they shade it in. Okay, so let me kind of explain how to do that. Let's take a look at these images, colored images right here that we have down here. So here is lead number 1. Okay. Here is lead number 1. What you do is find lead number 1, and then what you do is draw a perpendicular line to lead number 1. Okay? Then what you do after you go ahead and you draw a perpendicular line to lead number 1, if lead number 1 is positive or it's headed more towards the positive side, then you're going to shade this whole entire area. Okay, so one more time, draw a perpendicular line to lead number 1. This is going to represent the positive side, and then this side is going to represent the negative side. Shade the whole entire area, that's representing the positive side. Next, find your AVF. Here is your AVF. So your AVF goes down like that, okay? After you draw your AVF line, one more time, draw a perpendicular line to your AVF. Next, what you want to do is you want to go ahead and you want to shade in, okay? You want to shade in the area. So for AVF, you guys, this is going to be the positive side, okay? This whole entire side is the positive side. Let me just kind of write it for you. So one more time, here we go. So your AVF is going perpendicular, positive 90 to negative 90. Draw a perpendicular line to it. This whole entire side is going to represent the positive side, and this whole entire side is going to represent the negative side. What am I going to do? Well, I'm going to shade this half. Why am I shading this half right here? Because my AVF was positive. So I'm going to shade the lower half. Okay. Then try to superimpose the two shaded areas for lead 1 and lead AVF. So remember how we shaded this whole entire area for lead number 1? Okay. Find the area. Okay. So let me go ahead and kind of show you. Find the region, which is going to be right here, that basically has the shading for both lead 1 and lead AVF. And so as you can see right here, this part is going to be where you're going to have your mean electrical axis, which is again 0 to 90. And as you can see, we already figured it out right here when we drew our vectors, and we also said that your mean electrical axis is going to be 0 to 90 degrees. Okay, so one way is either to draw the vectors, okay, to figure out your mean electrical axis, or another way of doing it is go ahead and do the shading. Okay, let's take a look at another example together. Let's take a look at another example together to figure out the mean electrical axis. We are going to use lead 1 and we're going to use lead AVF. You want to take a look at lead 1, and one more time, you want to go ahead and take a look at the R wave and compare it to the S wave. Same thing, you're going to take a look at lead AVF and compare the R wave to the S wave. Over here, we can see that our R wave definitely has a way higher amplitude compared to our S wave, and so that would mean a positive vector direction. If you take a look at AVF, notice how the S wave is the one that has the higher amplitude, so that would mean a negative vector direction. So what we're going to do is you're going to go to the hexaxial axis that you have right here, find lead 1, so here is lead number 1, and draw your vector in the direction that you've determined earlier. So I'm going to go ahead and draw it in the positive direction right here. I'm going to find AVF, which is down here, or basically it's the whole like perpendicular line from positive 90 to negative 90. And since it is headed in a negative direction, I'm going to go ahead and I'm going to draw my my vector towards the negative 90 degrees. Why negative 90? Because this time I am heading in the negative direction. Okay. After you go ahead and you draw both of your vectors, go ahead and draw your mean electrical axis in between. So as you can see right here, in this case, your mean electrical axis is anywhere from 0 degrees to basically negative 90 degrees. Okay, so anywhere from 0 to negative 90, that's going to be your mean electrical axis. Now, if you remember, we said that your normal range should be from negative 30 to positive 90. So therefore, our mean electrical axis is not really within that normal range, because the normal range, let me just kind of highlight it for you. So the normal range is right here from -30 to +90. That's where we're supposed to be. Okay, anywhere from -30 to +90 is considered normal. Notice how we are not really within that normal range. We are from 0 to -90. Now, before I explain what could that mean, let me just kind of show you the second way that we did it, the highlighting version of how to figure out your mean electrical axis. So one more time, here is your electrical number 1, okay, or lead number 1. As you remember, draw a perpendicular line to it. This side is going to be the positive side. This side is going to be the negative side. Go ahead and shade in the positive side since we already determined that. Next, you are going to go ahead and find AVF. So AVF is right here. Goes from +90 to -90. Do the same thing. Draw a perpendicular line to your AVF. We said that the bottom half is positive, the negative half is negative. So this time I'm going to shade the negative half right here. Then what you need to do is try to superimpose the two shaded areas together. So I'm going to go ahead, try to superimpose the two. And what you're going to see is right in this region, this is where both of them meet. So one more time, you get to the same answer, which is your mean electrical axis is going to be in this quadrant right here, anywhere from 0 to -90. So basically, if I shade it for you right here, so we know that based on this information from our EKG, we know that we are somewhere right here, anywhere from 0 to -90. Now, there's a possibility that this individual might have something known as LAD, left axis deviation, and that's when your mean electrical axis gets shifted more towards the left. Because remember how normally we are supposed to be from 0 to +90. And you can see that our mean electrical axis got shifted more towards the left. Now, what are some reasons why your mean electrical axis could actually shift a bit to the left? Well, it could be due to pregnancy. So actually pregnancy can cause that. Obesity can cause that. Now, we consider the left axis deviation to be definitely to be problematic or to be of a concern if your mean electrical axis is less than -30 degrees. So if it's less than -30 degrees, then there could be like other reasons for it. One, it could be that your left ventricle is enlarged due to systemic hypertension or aortic stenosis. Those could be reasons behind it. Let's go ahead and take a look at another example together. Okay, so let's take a look at this example together. So one more time, we're going to take a look at lead 1 and AVF. As you can see right here, the S wave is definitely has a higher amplitude compared to the R wave. So what does that tell us? It tells us that it's going to be headed in, the negative direction. Now, if we take a look at AVF, let's take a look at AVF together. Here we go. Here is the R wave. The R wave seems to be the one that has the higher amplitude. so it's going to be headed in the positive direction. Okay, what are we going to do? We're going to go to our x-axial axis that we have right here, find lead number 1. Now this time you guys are going to draw your arrow headed this way. Your vector is going to be headed this way because we said that it's headed in the negative. It has a more negative deflection, so you're going to draw the arrow this way. Your AVF, here is your AVF, positive 90 to negative 90. I'm going to draw my arrow headed downwards. Why downwards? Because it is positive. Okay, so I'm going to go ahead, draw my arrow towards the positive 90 because it has a positive deflection. Okay, I drew my 2 vectors. Next, what I'm going to do is draw the mean electrical axis in between. So right here, we have this is your mean electrical axis, which tells you that your mean electrical axis is anywhere from positive 90 to 180 degrees. Okay. Now, as you can see, we are totally off the normal axis. The normal axis, we're supposed to be anywhere in between negative 30 to positive 90. And as you can see, we totally shifted towards the right from positive 90 to 180 degrees. Before we talk about what could be some possibility or reasons behind shifting towards the right, let's just go ahead and show you the quadrant shading method. So here is lead number 1. One more time, draw a perpendicular line to it. Here's the positive side, here is the negative side. So you're going to go ahead and shade the negative side. Find AVF. So here is AVF. Draw a perpendicular line to AVF. This is negative, this is positive. Shade in, let me just choose a different color. Okay, shade in the AVF, okay, the positive side. And then what you want to do is try to superimpose the two. Find the area that you have that has shadings from both lead 1 and AVF. So you can see right here, we get the same answer from positive 90 to 180. And let's go ahead and shade it on this axis right there so we can kind of see it. So it tells you that right here, this is where you have your mean electrical axis. Now, as you can see, we are totally off from our normal axis. And so that could be what we refer to as RAD. What is RAD? RAD stands for right axis deviation. Now, could someone have right axis deviation and it could still kind of be like a normal thing? Yes, especially children. Okay, so children can actually have a shift to their mean electrical axis, and usually their mean electrical axis is shifted towards the right, and that's absolutely normal. Another individuals that can also have a shift to their mean electrical axis towards the right are thin individuals. Okay, so thin individuals and children can actually have a right axis deviation. And when I say children, I should be more precise. It's usually like in newborns and infants, really. Okay, so usually infants, newborns, they usually have a right axis deviation. And so, and as I said, like, you know, normal, another thing is like thin individuals can have it. Now, are there some other problematic reasons why you might have a right axis deviation? Yes, if you have your right ventricle enlarged. Due to reasons like COPD, Like if you have your like a mitral valve or tricuspid valve lesion, that can cause right axis deviation. Let's go ahead and take a look at another example together. Okay, so let's go ahead, take a look one more time. Lead number 1. You can kind of see that the S wave is the one that has a higher amplitude. And I mean, in this example, you can't really see other than the S wave. It's not the best. But then again, some people have that. And then right here, the AVF also has a negative deflection. So in this case, it's a negative deflection right here, another negative deflection right there. What are we going to do? We're going to go to our axis. Here is lead number 1. I'm going to have to draw it in this direction, okay, right here, okay, for our lead number 1. For lead AVF, here is lead AVF. I'm going to also draw it up here towards the negative 90 because it also has a negative vector. Okay, after I drew my vectors for lead 1 and AVF, all you gotta do is go ahead and draw your mean electrical axis in between, and that tells you that your mean electrical axis is within this quadrant right here. So let's also shade it right here. So we're saying that this is where you have your mean electrical axis. Again, are we way off compared to the normal electrical axis? Yes, we are. The normal is anywhere from -30 to +90. And as you can see, we are from -90 to 180 degrees. So this could be an indication of extreme axis deviation. This is very, very rare, and actually most of the time it could be just due to placing the electrodes actually incorrectly. It can cause such an altered deviation. Let me just show you the method of shading it. So let's go ahead, shade it in together. So one more time, find your lead 1, draw perpendicular line to it. Here is your positive, here is your negative. We're going to go ahead, shade the negative side. Find your AVF right here. Draw a perpendicular line to it. Positive half, negative half. Shade the positive half. Superimpose them, and you're going to see that they're going to superimpose right here from -90 to +180.